Smart contract security, protecting your assets. Smart contract security is crucial for safeguarding assets and ensuring the integrity of decentralized applications. This comprehensive guide explores common vulnerabilities, best practices, and techniques to mitigate risks and create secure smart contracts. From using the SafeMath library to preventing overflows to implementing proper access control and avoiding re-entrancy attacks, developers will learn how to build robust and resilient smart contracts. What is the need for smart contract security, one might ask? So, usually what happens with smart contracts is it's a lot of sensitive information. Like you must have heard, right, that blockchain tokens, which have significant monetary value, someone coming and just taking 20 tokens from the blockchain might not seem like a lot, but it can translate to 20,000 American dollars, which is quite the high value, right? So you need to ensure that your smart contract that you have developed on the blockchain follows certain security procedures and protocols, right? Okay. So next we'll explore the common vulnerabilities in smart contracts. We have to learn how to identify common vulnerabilities such as reentrancy, integer overflow slash underflow, improper access control, and unchecked external calls. So we'll briefly go through all of them once. I'll just give you a brief introduction. We're going to cover each of them in great detail, where I'll give better examples and explain it in a more comprehensive manner. But to briefly go through it, the first type are re-entrancy attacks. So what are re-entrancy attacks, you might ask? So these re-entrancy attacks occur when an external contract calls back into the original contract before the initial function execution is complete. This can lead to unexpected behavior and potential theft of funds. This type of attack is a type of vulnerability that occurs in a software or in a function which is expected to be non-reentrant. That means it should not be called again and again till the previous invocation has been completed, right? If such a function, even though it's not supposed to be called again, is invoked recursively or concurrently, this will lead to unexpected behavior and potentially harmful consequences. Okay, moving to the next one. Integer overflows slash underflows. As the name suggests, what integer overflows and underflows are, right? Arithmetic operations may produce incorrect results when values exceed the maximum or minimum representable values, right? Okay. Next is improper access control. This is, as the name explains, it's very simple to understand. One with the wrong intentions has access to your smart contract. They can perform sensitive actions, and this can lead to potential exploitation and loss of assets. The next one is unchecked external calls. So, failing to handle external calls safely can lead to unexpected behavior and potential vulnerabilities, as external contracts may not execute as intended or may consume excessive gas, which eventually leads to losses. So, the first one is using SafeMath library to prevent overflows. Integer overflows and underflows can lead to unexpected behavior and again, security vulnerabilities. The SafeMath library provides functions to safely perform arithmetic operations without exposing us to these vulnerabilities. What is the SafeMath library, you might be asking? The SafeMath library is a collection of functions that perform arithmetic operations with built-in overflow and underflow checks, ensuring that the results are within the valid range of the data type. You must have already explored libraries in other programming languages, right? In C, C++, Python, Java. You import different types of libraries or pre-existing libraries. Similarly, even Solidity has the SafeMath library and multiple other pre-existing libraries. So this ensures that there is no unexpected behavior and security vulnerabilities don't take place. Okay, so next we'll go through the code example that the first statement is the import statement. We import the SafeMath library from OpenZeppelin. This library contains safe arithmetic functions. The next is the contract declaration as shown. It defines a contract named SafeMath example. Then we are using the directive. This declares that the contract will use SafeMath library for uint 256 operations. Next, we have defined the safeadd function. This defines a function called safeadd, which takes two uint 256 parameters a and b and returns their sum. The add function from SafeMath is used to perform the addition operation. So the add function is an already existing function in SafeMath, and we are using this function of SafeMath to perform the addition operation. Similarly, exactly same is your SafeSub function, but instead of addition, you do subtraction. right? The sub function from SafeMath is used to perform the subtraction operation. Next, ensuring proper access control. Proper access control ensures that only authorized users can perform certain actions. This can be implemented using modifiers like only owner. So this is very basic, right? For example, you have a shop, you're the owner of a shop, right? So all of your workers will not have access to the cash register, right? The janitor or someone who's just working the counter will not have access to your cash register. Only your cashier, you, the owner, and your few trusted employees will have access to the cash register. Similarly, to your smart contract, very few people will have access to certain functions in your smart contract, right? So, again, ensuring proper access control has three major steps. The first one is to identify roles, determining the roles and permissions required for your smart contract, such as owner, administrator, user, right? And then you just implement the access control. Use modifiers like only owner or role-based access control mechanisms to restrict access to sensitive functions based on the user's role or authorization level. You might be asking, what is the only owner modifier? We'll go through the code example. That should clear everything up for you, right? So again, in this first, we are importing using the import statement, we import the ownable contract from the OpenZeppelin library. This contract provides basic access control mechanisms, okay, allowing certain functions to be restricted to the owner of the contract. So again, we are importing a contract called ownable from the OpenZeppelin library. This gives us basic access control mechanism. And then it's just the contract declaration, which is contract is called access control example. Next is the stage of inheritance. You might have already explored inheritance in other programming languages, right? Inheriting one thing from another. So the contract we have defined, which is access control example, contract inherits from the ownable contract. This means that the access control example contract inherits all the functions and state variables defined in the ownable contract, including the only owner modifier. Okay, so the use of the only owner modifier will be showed in the next function, which is the restricted function. This defines a function named restricted function. The only owner modifier restricts access to this function so that only the owner of the contract, the account that deployed the contract, can execute it. This helps enforce access control, ensuring that sensitive functions are only called by authorized parties, right? So let's move to the next one. Avoiding reentrancy attacks. So reentrancy attacks, like even though I have explained it to you in technical terms, you might still be getting confused what these are exactly, right? So I'll take a very simple analogy that was very useful for me when I learned this concept, right? So these are very simple terms. Okay, so imagine you're at a bank and you ask the teller, the person at the bank, to withdraw money from your account. While this person is withdrawing money from your account, right? He's processing your request. You quickly ask him to withdraw more money multiple times before they finish the first request. This will create a lot of confusion to the teller and he might end up giving you more money than he should have. Right? So, for example, let's say I have 500 rupees in my account. I go to the teller, I say I want to remove 100 rupees from my account. By the time he goes and gets 100 rupees cash, I tell him seven more times that I want 100 rupees again, I want 100 rupees again, I want 100 rupees again, right? I'll keep repeating this. He'll get extremely confused as to what to do, and he might bring up 700 rupees. Now, this is an error, right? This is a loophole that I'm exploiting. I only had 500 rupees in my account, right? I took out 700 rupees, even though I have only told him that 100 rupees have to be taken out from my account. So the system will register my account balance as 500 minus 100, 400, even though I have 700 cash in hand. They occur when an external contract calls back into the original contract before the initial function execution is complete. This can be prevented using the checks effects interactions pattern. So you use CEI to remember this. So checks. First, perform all necessary checks and validations to ensure that the function can be executed safely. Second, E for effects. After the checks are successful, update the state variables and perform any necessary internal operations. Third, I for interactions. Finally, interact with the external contracts or perform any external operations such as ether transfer or external calls. Okay, next are like we'll talk about secure ether transfers. Secure ether transfers can be done using send or transfer methods, which have a fixed gas stipend and throw an error if the transfer fails, right? What is the transfer method, you might be asking? The transfer method is a built-in function in Solidity that sends ether to a specified address. It automatically reverts the transaction if the transfer fails, ensuring that the contract state is not updated. Like how a postal system works, right? You give a fixed address to deliver your letter to, your envelope to, and automatically takes the letter back. It does not deliver it if it finds that the address does not exist. It reverts the delivery of the envelope if it finds the mailbox, the particular address does not exist. So similarly, it sends ether to a specified address and it automatically reverts the transaction if the transfer fails, ensuring that the contract state is not updated. Okay, so let's go through the code example that should clear a lot of things up for you. Okay, so first is contract declaration. We are just declaring a contract named secure transfer. Okay, next is the definition of the safe transfer function. So we define a function named safe transfer. It takes two parameters. First being the recipient, the address of the recipient to whom ether will be transferred, right? To whom you're sending the mail, essentially, right? You need the address of that person. It is also specified as payable, indicating that the address can receive ether. So you're showing that the mailbox you're sending your envelopes or letters to, right? It should be free to receive envelopes or letters. It's not already full. It's not blocked, like blocked up from receiving letters, right? So it's indicated by payable that the address can receive ether. And amount is clear, obviously the amount of ether to transfer. So here we have also added a require statement. So you might recall require statement from the last video. So this checks if the contract's balance is sufficient to cover the specified amount of ether. If the balance is not enough, the function reverts with the error message insufficient balance. This ensures that the contract doesn't attempt to transfer more ether than it holds. Right? And finally, it's just the transfer method. If the balance check passes, the function proceeds to the transfer and the specified amount of ether amount to the recipient address using the transfer method. Right? And this transfer method is considered safe as it forwards only a fixed gas stipend, limiting the potential for reentrancy attacks. Okay, let's go through the next one. Handling external calls safely. So these are your basic guidelines you have to follow with external calls, right? While calling external contracts, it's important to handle failures and limit the gas forwarded to prevent unexpected behavior. Check for success. Always check the success status of external calls and handle failures appropriately. Like make sure, like for example, you're sending a letter to someone, make sure it's delivered, right? You have to check the success status of these external calls. And if it's not delivered, like if there's failure, you have to handle them appropriately. Limit gas, limit the amount of gas forwarded to external calls to prevent excessive gas consumption and potential vulnerabilities. So while you're sending a mailman with letters, right? Make sure you're only giving him a specific amount of letters. If I've, like, let's say I've given a mailman 100,000 letters to deliver in one day, he might get confused, right? And a lot of gas will be consumed. Like, gas is essentially resources, energy. And this also leaves us to potential vulnerabilities. So, we should always limit the amount of gas forwarded to the external calls to prevent excessive gas consumption. And third is again secure coding practices, right? You should always keep these in mind. Follow secure coding practices such as using the latest Solidity version and auditing your code regularly. Okay, so finally, we'll just walk through a comprehensive example that integrates various best practices into a single smart contract. Okay, let's go through this. First are the import statements. Import opens Upland's ownable contract for access control and SafeMath library for safe arithmetic operations. We have already talked about these individually before. Now we are taking them together. Again, next is what you have already got used to, contract declaration. Defines a contract name secure contract. Using directive, like I told, enables the usage of SafeMath library for uint 256 operations within the contract, right? Now we have the state variables, balances, a mapping that associates addresses with their balances. It stores the ether balance of users. Next, we have our events. Deposit. An event emitted when a user deposits Ether into the contract. It logs the user's address and the amount deposited. Withdrawal. An event emitted when a user withdraws Ether from the contract. It logs the user's address and the amount withdrawn. Like, it's very obvious from the name, but these are what these events do. So next are the deposit and withdraw functions, right? So the events are different, right? And the functions are different. Please keep that in mind. So once I explain the functions, the difference between the events and the functions should be clear. But if you have any more doubts, you can always explore these on your own. And you should make sure that the difference is clear between you. I have tried my best to explain it, but okay, here we go. The deposit function allows users to deposit Ether into the contract. It increases the sender's balance in balances mapping by the amount of Ether sent in message.value, right? So the deposit function emits a deposit event to notify listeners about the deposit. So the function is emitting a deposit event to notify listeners about the deposit. Please pay attention on this line. The function will emit an event to notify listeners about the deposit. Withdraw function allows users to withdraw Ether from their balances. It checks if the withdrawal amount is less than or equal to the sender's balance. So we have put a check in place here to check if the withdrawal amount is less than or equal to the sender's balance, right? Now we have the withdraw function, right? It's pretty similar to the deposit function, except we have also put a check over here. Let's go through it. The withdraw function allows users to withdraw Ether from their balances. It checks if the withdrawal amount is less than or equal to the sender's balance. This is the check we have put in place here. This was again the checks, effects, interactions pattern, right? That we went through before. So this is the check we have in place. So the withdraw function will decrease the sender's balance in the balances mapping by the withdrawal amount, and it transfers the specified amount of Ether to the center. So this withdraw function emits a withdrawal event to notify listeners about the withdrawal, right? So carefully, the withdraw function ending with a draw, DRAW draw, emits a withdrawal event ending with a AL, right? To notify listeners about the withdrawal. So there should not be any confusion between the withdraw function and the withdrawal event. These are different things. They are pretty similar, but still different. And this difference should be absolutely clear. Withdraw is a function ending with AW, and withdrawal is an event ending with AL. Next, we simply have a restricted function which implements access control and ensures only the contract owner can execute this function, right? And finally, we have the external call function. This allows the contract owner to make external calls to other contracts and transfer Ether. This uses the low-level call function with a limited gas amount to prevent potential re-entrancy attacks. It also checks if the external call was successful and reverts the transaction if it fails. So it's using a low-level call function with a limited gas amount. Keep that in mind. We already discussed this, right? Limiting the gas amount. So this is to prevent potential re-entrancy attack. So this is it essentially. This contract basically provides basic functionalities for users to deposit and withdraw Ether securely, along with access control mechanisms and the ability for the owner to make external calls to other contracts. And that's it. I guess we are done. See you in the next one.